Welcome to Summarize Science. We know that neural networks are famously nonlinear, which is what makes them so powerful at complex tasks. But that complexity also makes them hard to analyze and control. This paper asks a radical question. What if we could find a new mathematical framework where these complicated networks are actually perfectly linear? The researchers introduce a new architecture they call a linearizer. The core idea is to take a simple linear matrix, A, and sandwich it between two special, invertible neural networks named G_X and G_Y. These G networks act like mathematical translators, warping the data into a new space where everything behaves linearly. In this new space, complex operations become as simple as adding and scaling vectors. So, what can you do with this? One of the most exciting applications is in generative models like the ones that create AI art. These models usually take hundreds of small steps to turn random noise into a final image. Using the Linearizer framework, the researchers show how to collapse all of those hundreds of steps into a single matrix multiplication. This means generating an image can be done in just one step, which is a massive speedup. This method also solves a major problem with diffusion models. They're usually a one-way street. It's hard to take a final image and figure out the exact noise it came from. Because the linearizer is perfectly invertible, you can now go backwards with complete accuracy. This allows for amazing feats like creating perfectly smooth interpolations between two different real photos by mixing their latent codes. The power of linearity also makes things like style transfer incredibly simple and modular. Here, each artistic style is just represented by a different matrix. You can apply a style to a content image with a single pass, or even linearly blend two style matrices together to create a smooth transition between them. So, let's quickly recap what makes this framework so powerful. First, it collapses hundreds of generative steps in diffusion models into one, making them incredibly fast. Second, it makes these models perfectly invertible, which unlocks precise editing and seamless interpolation between images. And third, it allows for modular control over things like artistic style, treating them as simple building blocks. By making complex models behave linearly, this work provides a powerful toolkit for building more controllable, understandable, and efficient AI. It opens the door to future models that are not only expressive, but also have the elegance and predictability of linear algebra.